equation. Okay. طيب, let's go today and let's define actually the different terms in the first law of thermodynamics. First of all, we'll just define the concept of energy transfer and the different forms of energy that the system can possess. Also, we'll look at the forms of energy transfer. As we said, energy can transfer by heat. We'll consider the different mechanism of energy transfer, by heat. Heat can transfer by conduction, heat can transfer by convection, and also heat can transfer by radiation. Also, we'll move to the form of energy transfer by work, including actually different forms of mechanical and electrical work, spring work, different kind of work actually will be defined. And inshallah, at the end, we will define actually the energy transfer, the forms of energy transfer by mass. Then in this case, we have defined all of the terms in the first law of thermodynamics. Then we can apply either for closed system or for open system. So inshallah, also will be developing the first law of thermodynamic equation for closed system, and also will be developing the equation in case when we have an open system. Type here is just the introduction and test your understanding to the first law of thermodynamics. We said based on the energy cannot be created or destroyed, the first law of thermodynamics came up and it say energy input to the system will equal to energy output plus the part of energy stored within this system. Okay, type if we look at actually this example, we have a fridge inside a room. This room is totally insulated, so don't have any form of heat transfer outside this room. And in this case, actually, we are opening the door of this fridge into the room. So what will happen in this case actually to the air temperature inside this room? So in this case, if I look at this system, this is actually a system. Let's move to the zoom window. Okay, so if you look at this room as a system, as a thermodynamic system. Okay. Okay. So let's consider this room as this system. This is actually a system, and we have energy input to this system, and we have energy output of this system, and part of energy is stored within this system. If you look at this room, we have actually energy input in the form of work. But do we have any form of energy out? We don't have energy out. That means actually if we apply the first law, energy in minus energy out will equal to the change of energy of the system in this case. As it is an isolated room, we don't have energy output, so all of the energy input to the system will be just stored within the system, and it will result in what? It will result in this case in temperature rise of air. As we open the door of this fridge, actually it will be cooling down the air inside this room. But if you look at the back of the fridge, usually the function of the fridge is to absorb actually the heat from the food compartment, and then it rejects it actually through the condenser in the back of the fridge. So there is a condenser in the back of the fridge in which actually we reject this heat. So for the fridge, it is inside the same room. So we absorb the heat from one location and reject it inside the same room. And the heat rejected is higher than the heat absorbed. Efficiency is less than 100. So at the end, actually, the temperature of the air will be raised. Another example here, we have a fan inside also an isolated room. This fan is running. Also, the temperature of the air inside this room actually will be raised in this case. Because if we look at this room as a system, we have energy input, but we don't have energy output. So all of the energy input will be stored within the systems, and it will result in temperature rise. So it is advised actually if you have a fan running a fan or something to open the window, so that actually part of the heat that is generated due to friction, the kinetic energy of the air will be dissipated in the form of heat due to friction between the molecules and between the moving air and the wall. So at the end, the kinetic energy of the gases will be just kinetic energy of the gas will just hit the wall, and at the end it will be dissipated in the form of heat. So in this case, it is advised if you have a fan to open a window or something, so actually part of the energy stored can leave the system, so that actually you can enjoy some cold air in this case. So the idea is that it is an energy balance. Energy cannot be created or destroyed. So if we have energy in, then it should equal to energy output plus the part of energy stored within this system. Okay. طيب, what are the forms of energy that the system can possess? We'll look at actually in this chapter, inshallah, we'll be looking at those terms, energy in minus energy output equal to the change of energy of the system. Energy in or energy output are the forms of energy transfer, and we said energy can transfer by heat. Whenever we do have actually energy can transfer by heat, whenever we have temperature difference delta T between two systems, then energy can transfer by heat. Energy can transfer by work, W, by work, whenever we have a force multiplied by a applied force and we have a movement, then in this case we can have work, and we can have actually energy transfer by mass. When we have a flowing fluid, then we can have energy transfer by mass in this case. But this term, ya shabab, is equal to 0 in case when we have a closed system. Because closed system, it does not allow for mass transfer at all. So we don't have mass transfer. That means actually we don't have energy transfer by mass in case when we have a closed system. Okay. So what are the forms of energy? Change of energy of the system. What are actually the forms of energy that the system can possess? This term actually is classified either macroscopic form of energy, macroscopic, which actually is a forms of energy that the system can possess in whole as one part, like the moving car in this case. So if we have a car is a moving in this case, so it has kinetic energy. So kinetic energy is actually one form of the macroscopic form of energy. Kinetic energy is equal to half m multiplied by the velocity v squared. Okay. Also under macroscopic form of energy, if this car is moving on an inclined road or something, so that means it is accepting potential energy because the elevation z is increased in this case. So that means also we have another form of macroscopic form of energy, potential energy, which is equal to mass multiplied by gravitational acceleration g multiplied by the elevation z. This is macroscopic form of energy that the system can possess actually as one unit. There is another form of energy which is called the microscopic form, or the internal energy of the system related to the temperature of the system. So the other form of energy that the system actually can possess is called the microscopic, not macroscopic. Microscopic actually is related to the molecular activity of the system. Molecules can move in the form of kinetic energy, can have actually translational motion, rotational motion, vibration also is one form. The summation of all of these forms of energy is called as actually the internal energy U. Okay, so the energy, the forms of energy that the system can possess are actually kinetic energy, half mv squared, potential energy mg multiplied by z, and the internal energy U, which is mainly function of the temperature. If the temperature is high, that means actually the internal energy is high in this case. So if we have a system in this case, and we need to apply the first law of thermodynamics, then it will be energy input minus energy output equal to change of energy of the system, and the total energy of the system is equal to the internal energy U plus the kinetic energy plus the potential energy. So it will equal to internal energy U plus kinetic energy half mv squared plus potential energy, which is mg multiplied by z. This total energy is calculated in kilojoule. This is the total energy. Okay, so this term is calculated in kilojoule. In this course, inshallah, we are concerned with the specific property. We don't look at actually the total mass, just we need to know the specific property, which is the property per unit mass. So the specific energy of this system, which is the energy divided by mass, will equal to the specific internal energy plus half v squared just divided by mass plus g multiplied by z. And in this case, the specific energy, all of these terms are calculated actually in kilojoule per kilogram. So this term is calculated in kilojoule per kilogram, and also like this actually the other terms. But just to keep in mind the internal energy in kilojoule per kilogram, this will be from the tables, inshallah. We'll learn how to calculate. But this term, if the velocity is in meter per second, this term will be actually in joule per kilogram. So inshallah, we'll be talking about this later on. So this term has to be multiplied by 10 to the power 3, and this term has to be multiplied by 10 to the power 3, so that actually their unit should be kilojoule per kilogram. Okay. But usually when we are studying a system, we don't look at actually the energy at the given state, because at a given state, we cannot have heat transfer, we cannot have work, cannot have anything actually, any form of energy transfer. The system should undergo actually a process or cycle, so that actually we can have a change of energy and we can have actually mass transfer. So if we have a system undergo a process, let's say from state 1 up to state 2, then in this case actually we can say the change of energy of this system will equal to change in what? Change in internal energy plus a change in kinetic energy plus a change in potential energy. So that should equal to U2 minus U1 plus half M multiplied by V2 squared minus V1 squared plus mg multiplied by the difference in elevation Z2 minus Z1. And this is the change of the total energy of the system. This is in kilojoule. Again, we need actually the specific change of energy of the system, delta E of a system, we have to divide by mass, will equal to U2 minus U1. This is called as a specific internal energy. As we said, this term is the specific internal energy, kilojoule per kilogram, which is the same as unit. Delta E is kilojoule per kilogram. This is called E small, the specific energy. E capital is the total energy in kilojoule. E small is in kilojoule per kilogram. This value, U2 minus U1, will be inshallah calculated from tables. We will learn inshallah in chapter 3 how we can calculate U2 and U1 mainly as function of temperature. This is called the specific internal energy. Plus, just to divide this term by mass, it will equal to half V2 squared minus V1 squared plus J multiplied by Z2 minus Z1. And this is actually the change of a specific energy of a system when it is actually undergo a process from initial state to a final state. Okay. Type, there is a special case. Or let's calculate first of all, this is the energy. How we can calculate the power of the system? So the power of the system, power is equal to what? The rate of energy, or energy per unit time, or we call it actually as energy dot. So it should equal to mass, energy is mass, multiplied by total energy. Right? It is, yes. So it is the energy per unit time, and the energy actually is equal to mass, or the change of energy delta E per unit time, mass multiplied by the change of specific energy divided by time. And the mass over time, we call it actually M dot, which is actually the mass flow rate. So it will equal to the mass flow rate, M dot, multiplied by the change of energy of the system. Type mass flow rate is what? If we have a flow inside a tube or something, just a flow inside a tube, this tube actually has a cross-sectional area which is normal to the velocity, normal to the flow direction, the area normal to the flow direction. We have the mass is defined as what? Mass is defined as the density multiplied by the volume. Okay. So in this case, mass flow rate M dot will equal to what? Mass divided by time it will be actually M dot will equal to mass rho V divided by time. V over time we call it actually as V dot. V dot is the volumetric flow rate calculated in meter cube per second. Okay, and the volumetric flow rate is equal to the cross-sectional area multiplied by velocity. So M dot is equal to density multiplied by area. M dot is density multiplied by area multiplied by the velocity. So in this case, the power of a system will equal to M dot multiplied by the change of energy of the system, U2 minus U1 plus half V2 square minus V1 square plus J multiplied by Z2 minus Z1. And this is actually the power of the system. Power is just the rate of energy per unit time. So it will equal to mass multiplied by specific energy divided by time. Mass over time is called as actually the mass flow rate. Mass flow rate is equal to the rate of change of mass per unit time. Mass is rho V, so it will equal to mass flow rate is rho V dot. V dot actually is the volumetric flow rate, and I think you know about this. Volumetric flow rate is equal to the cross-sectional area of the flow, normal to the flow direction, which is actually multiplied by the velocity. V dot is area by velocity, so the total mass flow rate is density multiplied by area multiplied by velocity. Mass flow rate is the mass per unit time, which is calculated in kilogram per second. So that actually this power is calculated in kilowatt, and this change of internal energy again is in kilojoule per kilogram. We set this term velocity in meter per second. We have to divide by 10 to the power 3, so that actually all of these terms are just calculated in kilojoule per kilogram. Okay. Those values of specific internal energy we can get inshallah using the table as we will learn inshallah in chapter 3. So that's all actually about the term, the change of energy of the system, which should equal to the change in internal energy, change in kinetic energy, plus the change in potential energy. We have a special case actually, which is common case actually for a stationary closed system. When we have a stationary closed system. Stationary means actually the system is not moving, so we don't have a change in velocity. V2 is the same as V1, it is not moving. And although we don't have a change in potential energy, so the potential energy will equal to 0. So in this case, actually, the change of energy of the system will equal to what? The change of internal energy delta U. So in this case, the term delta U of the system will just equal to the change of internal energy U2 minus U1, or we can just consider it in the specific form. It will equal to mass multiplied by U2 specific internal energy U2 minus U1. Okay, this is for a stationary closed system, and most of the closed system are actually a stationary system. So inshallah, when we see the first law of thermodynamic equation for a closed system, energy M minus energy L is equal to the change of energy of the system. In most of the cases for a closed system, this term delta U of the system will be just reduced to mass of the system multiplied by the change of the internal energy U2 specific internal energy at the final state minus U1, which is the change of the specific internal energy at state 1. Type, this is actually what we said, what we have defined on the board, the total energy of the system and the energy by mass, and then we can calculate the change of energy of the system. Type, we said for a stationary closed system, as we said, the kinetic and the potential energy will be 0, and in this case, delta U of the system, this term actually in the first law equation will be just substituted by mass multiplied by the change of internal energy. Type, let's look at this example. Here actually this guy. So we need to determine actually the engine power required to accelerate this car from the rest. Rest mean actually the velocity V1 is 0 to 100 km/h in 5 seconds. So the initial velocity V1 is given, V2 is given, and time is given, and mass of this car actually is equal to 800 kg, and we need to calculate the power required to accelerate this car from the rest until actually the velocity is equal to 100 km/s, 100 km/h in 5 seconds. This is a very important parameter in the specification of any car. If you want to go to buy a car, it will just tell you about this number. This car can be accelerated from the rest up to 100 km/h in, let's say, 1.1 second, or let's say 2 seconds and 3 seconds. This is actually can be a good difference between any two cars. If this time is reduced, that means actually the engine power is very high and the system response is actually very fast for this car, other than the car that actually accelerate in longer time. طيب, in this case, I show this mass is given is 800 kilogram, and he said from the rest, so the velocity V1 is equal to 0, and velocity V2 is equal to 100 kilometer per hour. So kilometer, we have to multiply by 10 to the power 3. Per hour, we have to divide in this case actually by 3,600, which is 60 by 60. 60 to convert actually from hour to minute, and another 60 to convert from minute to second. Then in this case, it will be V2 equal to 100 multiplied by 10 to the power 3 divided by 3,600. And in this case, actually, the unit should be meter per second in this case. Okay. So this is V1, V2, and we have also time. Delta T is given is equal to actually 5 seconds. Okay. And we need to calculate the power of this system, power required to drive this system. So we said the power, we have defined actually as the power is equal to mass multiplied by the change of energy of the system divided by time. Power is the energy, total energy per unit time. Total energy is the specific energy, change of a specific energy multiplied by mass divided by time in this case. And this is equal to mass divided by time multiplied by the change of energy of the system, which is U2 minus U1 plus V2 squared minus V1 squared divided by 2 plus G multiplied by Z2 minus Z1. Okay, internal energy, actually we don't have a change of temperature. This car is running under atmospheric condition, so the term U2 minus U1 we don't have difference, is 0. V1 in this case is accelerating from the rest, so the velocity V1 is 0. And this is actually a horizontal road. We don't have a change actually in potential energy, don't have a change of elevation. So that means actually in this case the power to accelerate this car will equal to mass multiplied by V squared divided by 2 divided by 90. Mass is 800 and the velocity is 100. We said we have to multiply by 10 to the power 3 divided by 3,600. This is the velocity. This velocity is a square divided by 2, and we have also to divide by time, which is 5 seconds. Then we can calculate this power. This power in this case should be calculated in watt. Okay. If we divide this value by 10 to the power 3, if we divide the value, so that will be calculated in watt. If we divide it by 10 to the power 3, then we can get this value in kilowatt. There is another unit actually for calculating the power, which is the horsepower. We have 1 horsepower is equal to 0.75 kilowatt. So if we just actually divide this value by 0.75, then we can get actually this power in horsepower. Okay, because you may see actually this definition horsepower in some application. Okay, type this actually is related, as we said, actually to the forms of energy transfer of the system. We have kinetic energy, potential energy, and we have also the internal energy. We have another actually we have another classification of the forms of energy transfer. Energy can be classified actually as a static form of energy, which cannot actually cross the system boundary, and it cannot result actually in work out of the system or work generation from the system. And we have also the dynamic form of energy. The form is actually of energy that can cross the system, boundary. Okay, so energy classification of the forms of energy transfer. Energy can be classified as a static form of energy or dynamic form of energy. Static form of energy, which is the form within the system itself that cannot be transferred across the system boundary and generate work, like the internal energy. So the forms of energy transfer. We have a static form of energy which cannot cross the system boundary and generate work, like the internal energy. And we have the dynamic form of energy. Dynamic means actually it can cross the system boundary and it can generate work. The dynamic form of energy, like the heat transfer, can cross the system boundary, like the work can cross the system boundary, and also like the energy transfer by mass. If we have mass actually crossing the system boundary, then in this case it is a kind of the dynamic form of energy. Why actually static form of energy cannot generate work? Because the static form of energy or internal energy is related to the motion of the molecule, and the motion of the molecules, if you look here in the presentation, the motion of the molecules are actually a random motion. So one molecule is moving in one direction and the other molecule is moving in the reverse direction. So we cannot generate work in this case. So if you have very high temperature fluid water, and we put actually a turbine inside this water, this turbine cannot be rotated, even if the temperature of the fluid is very high. Because temperature is high, that means the internal energy is very high, but internal energy is a static form of energy. We cannot convert it into work. But actually, if we convert this static form of energy, this water, and at the bottom of a dam or something, we can pass it through a small cross-sectional area. Then in this case, the velocity of the flow, we can generate high velocity jet, high flow of high velocity or jet velocity in this case. Then we can convert this static form of energy, we can convert it to a dynamic form of energy in the form of kinetic energy. Then in this case, this kinetic energy can cross the system boundary, so we call it as dynamic form of energy, and it can hit actually the bucket of this wheel, of this turbine, then it can rotate it. So any form of energy that can cross the system boundary, it can generate work in this case. But the static form itself, the internal energy, whatever the value of the internal energy, it cannot actually rotate the system, because actually it is actually not organized form of energy related to the molecular activities, which are actually very random motion of the molecule, cannot result actually in the generation of the work in this case. Okay. So those are the forms of energy. We have a static form of energy, which is the internal energy, form of energy transfer. We have a static, not transfer, it cannot cross the system boundary. What can cross the system boundary are the forms of energy transfer by heat, energy transfer by work, or when we have actually energy transfer due to mass transfer. But what is the difference between heat and work? We can have energy transfer by heat when we have a change of temperature, difference in temperature. If I have actually two systems, one is at a temperature higher than the other system, then in this case we can have energy transfer by heat. Work, actually, other than this, the work actually, the form of energy transfer is work, and work, we can get work when we apply force and we have a movement, then in this case we can have work. And this is the difference between energy transfer by heat and energy transfer by work. Let's consider actually, inshallah, next class we'll be talking about the forms of energy transfer by heat, and we'll start also talking about the different kind of work. But let's start today, inshallah, with this term energy transfer by mass, starting with what's called actually the mechanical energy of the fluid. Mechanical energy of the fluid. Mechanical energy is the form actually of fluid energy, or a form of energy transfer by mass, or the part of the energy transfer by mass that can be converted actually to mechanical shaft power without the need of a heat transfer. So mechanical energy is the part of the energy of the flow of a flowing fluid that can be converted directly into work without having heat transfer. As we said, actually, to have a heat transfer, we have to have heat engine, like the engine of the car. And to have a heat engine, we have to have heat transfer, burn the fuel. To have heat transfer, then we can convert this heat into work. But if we have a moving fluid, then in this case, we have energy transfer by mass. Part of this energy transfer by mass, we call it the mechanical energy of the fluid, which can be converted into work without the need of the heat engine. Like actually this example, hydraulic turbine. We can have actually high velocity jet flow to hit the bucket, then we can generate work without actually having heat addition in this case. Okay, but if we have a flowing fluid inside a tube or something, we have a flow that is moving, let's say, from cross section 1 to cross section 2. What are actually the forms of the mechanical energy of the fluid? The mechanical energy of the fluid will equal to the flow energy plus the potential energy of the flow plus the kinetic energy of the flow. The flow energy FE, which is equal to actually the pressure multiplied by a specific volume. Actually, to have this flow moving from one location to another location, B1 to B2, that means actually the pressure B1 is greater than what? Greater than B2. And the pressure is acting normal to the flow and to inside of this system. So we have a pressure force is equal to pressure multiplied by area. Like this flow is moving from one point to another point. So that means it is moving distance L. So in this case, actually the work or the energy of the flow will equal to pressure multiplied by area, which is the force multiplied by the distance L. Area multiplied by distance L is the total volume. This is the total energy, which we call it the flow energy, due to the pressure, will equal to pressure multiplied by volume. So the specific flow energy will equal to pressure multiplied by a specific volume, and the specific volume is calculated in meter cube per kilogram, and this is the flow energy. Okay. In this case, we can just define the mechanical energy of the fluid. The energy of this fluid, it can have flow energy due to pressure, it can have kinetic energy if it is have velocity, and also it have elevation, so it have potential energy. So the mechanical energy of the fluid will equal to pressure multiplied by specific volume plus half V squared, which is the kinetic energy, plus the potential energy will equal to Gz. If this fluid is moving from one location to another, so the change of mechanical energy of the fluid delta E mechanical will equal to pressure B2 minus B1, specific volume is 1 over density. So it will equal to delta B, delta E mechanical will equal to delta B divided by rho plus half V2 squared minus V1 squared plus J multiplied by the change of elevation Z2 minus Z1. And this is the change of mechanical energy of the fluid when it is moving from one cross section to another cross section inside the tube. What about the power of the fluid? Power of the fluid in this case, power will equal to what? The rate of energy per unit time, energy per unit time. So it will equal to m dot or mass multiplied by specific energy divided by time. So it will equal to m dot mass over time is m dot. So the power of the flow in the fluid will equal to mass multiplied by delta E mechanical over time. M multiplied by delta E, which is the total energy. Okay. So mass over time, it will equal to m dot. So this will equal to m dot multiplied by delta E mechanical, or it will equal to m dot multiplied by delta E mechanical, which is B2 minus B1 over rho plus half V2 squared minus V1 squared plus G multiplied by Z2 minus Z. Okay. And this is actually the power. But just be careful again, as we said, if this pressure is in Pascal and this velocity is in meter per second and this elevation Z is in meter, then in this case this power will be calculated in watt, and this m dot is calculated in mass flow rate is calculated in kilogram per second. And this is actually the power of a moving fluid, of the mechanical power of a flowing fluid. So if we have a flowing fluid with a velocity V, and we have a change of pressure from one location to another under pressure difference, and also under this flow is moving from one elevation to another, then the total power of the fluid is equal to m dot multiplied by delta B over rho, the flow energy plus change in kinetic energy plus the change in potential energy. Okay. Here is an example. We have a hydraulic turbine. You know the idea of the hydraulic turbine. We put a hydraulic turbine at the bottom of the dam or something. So in this case, we can convert this potential energy of the fluid at the bottom of the dam will have high pressure flow. Then we can pass the flow actually through a small diameter cross-sectional area to have a velocity jet. Then this velocity jet actually can hit the bucket of the turbine. Then we can rotate actually the shaft of this turbine to generate electrical power. To calculate the power of this hydraulic turbine, we can just select one point of the fluid before point 1 and point 4 after this turbine. and then calculate actually the change of mechanical energy of the fluid, multiplied by the mass flow rate of the fluid, then we can calculate the power of this turbine. We call it actually work maximum because in this case we assume all of the fluid energy will be converted into mechanical shaft power. So in this case, the maximum work or the fluid power will equal to M load multiplied by the change delta E mechanical, 0.1 and 0.4. 0.1 at the surface of this fluid is actually at 0.1, the pressure is atmospheric. At 0.4, actually, after the flow is expanded inside this turbine, it just moved to the atmospheric. So pressure V1 and V4 is the same, V atmospheric. Velocity V1 and V4 at the top of the fluid is the same. So velocity V1 and V4 is the same. So in this case, the change of mechanical energy of the fluid will equal to the change of the potential energy. And the power of this turbine will equal to M dot multiplied by the elevation Z1 minus Z4. This is just an example. But if I select another 2 points instead of 0.1 and 4, let's say 0.2 here and 0.3. At 0.2 and 0.3, we can say same cross-sectional area, so it should be the same velocity as we have defined. M dot is density by area by velocity. If we have same mass flow rate, same density, and in this case, same cross-sectional area should be the same velocity. V2 is the same as V3. And 2 and 3, just before and after the turbine, we can assume no change in elevation. So in this case, actually, we can just define the work maximum or the change of energy of the fluid equal to M dot multiplied by B2 minus B3 divided by the density, or M dot multiplied by delta B over density in this case. And it should be this value should be the same as actually as this value. If I select 0.1 and 0.4 to calculate the fluid energy, it should result actually in the same value if I select another 2 points, let's say 0.2 and 0.3. And this is the idea that we can convert the mechanical energy of the fluid into shaft power. Okay. So let's end up with this example. Here he said we have a site is evaluated actually for a wind farm. Wind farm is used to generate electrical power using actually the wind energy. He said we have a site is evaluated to have a wind farm. So this is actually the idea here is that we can have a fan. This shaft of the fan is connected to an electric generator, and it is fixed actually to have free air is coming with high velocity. So air is coming with velocity, let's say V1. This velocity actually is high. Usually it is not applied in any location to have a wind farm. I think within K2BIM we have a wind farm. We have a fan is fixed close to the rig center. You can look at it there, where actually we have a high velocity there. From the high elevation to the low elevation, we have difference in elevation, so we have a kind of air velocity there. You can look at it there. The idea here actually is to have this fan. Air is coming with high velocity, so it will just actually rotate this fan, hit the bucket of the fan, the blade of the fan, then actually this fan will be rotating. Then we can generate shaft power. This shaft power we can connect to an electric generator to generate electrical power, in this case, work.electric. We can have current out of this system. He said this actually in this problem, V1, velocity V1 is equal to 8.5 meter per second. And after hitting the blade, usually the air will be leaving actually at velocity V2 much less than V1. Or we can say V2 will be almost equal to 0, okay? And we need to calculate in this case, we need to calculate the energy per unit mass. Energy per unit mass of the system, and we need to calculate also the total energy, and we need to calculate the power of this fan, A dot, rate of energy A dot. Okay. Type in this case, to calculate the energy of the flow. So let's say we'll have 2.1 here before this fan, and we have 0.2. Velocity V1 is given 8.5 meter per second. Velocity V2 is almost 0. Between 0.1 and 0.2, 0.1 and 0.2 just before and after this fan, Z1 is almost the same as Z2. We have the same elevation. And also, in this case, actually 0.1 and 2, usually the fan is fixed in the atmosphere. So the pressure V1 is the same as V2. So the power of the flow, or the change of mechanical energy of the flow, will equal to what? B2 minus B1 over rho. B2 is the same as B1, so this term is not there. elevation Z1 and Z2 are the same, so this term is not there. So the change of mechanical energy of the fluid will equal to the change of the kinetic energy of this case. So delta E mechanical will equal to half V2 squared minus V1 squared. V2 is 0, so the absolute value in this case will equal to half multiplied by the velocity 8.5 squared. Then we can calculate this velocity, this change of mechanical energy of the fluid in joule per kilogram. This is joule per kilogram. And we can calculate the power or the energy, the total energy, mechanical energy of the fluid will equal to mass multiplied by delta E mechanical. He said actually calculate the total energy if the mass is equal to 10 kilogram. So it will equal to 10 multiplied by half 8.5 squared. Then we can calculate it actually, the value will be calculated in joule. Okay. But if I need to calculate the power, then in this case it will equal to M dot multiplied by delta E mechanical. He said we need to calculate the power when the mass flow rate is equal to 1154 kilogram per second. Then the power E dot will equal to M dot multiplied by actually the change of energy mechanical of the fluid. It should be calculated in watt. If I want it in kilowatt, then we can just divide by 1000. Then we can convert this value into kilowatt.